Hello scholars, welcome. Mr. Hinkle here. Today we're going to discuss volcanoes. Volcanoes are where magma from underneath the surface of the earth erupts onto the surface of the earth, creating igneous, extrusive rock. And they come in a variety of types, shapes, sizes, compositions. But before we get into all of those details, let's just figure out what are volcanoes and where are they distributed on the surface of the earth. So today we will introduce the concept of volcanism and the driving force behind it. We will then get into the global distribution of volcanoes. Where are these things at? So, as mentioned, a volcano is when magma from underneath the surface of the earth erupts onto the surface of the earth as lava. Volcanoes create igneous rock. There are two types of igneous rock. Igneous intrusive, when the melt solidifies underneath the surface of the earth, and igneous extrusive, when the melt solidifies above the surface of the earth. So volcanoes create igneous extrusive rock. And in fact, that is basically the definition of a volcano. It is a land formation created when lava solidifies into rock. And for completion, we will say that lava creates an igneous extrusive rock. Excellent. So what is behind this? Well, in most cases, when you're talking about geology, if you want to know why something happens, you could throw your hands up and say plate tectonics. Because plate tectonics is the unifying theory of geology that explains dynamic Earth surface processes. And it states that the surface of the Earth is covered by large, rigid bodies of rock called tectonic plates. And these tectonic plates move around the surface of Earth relative to one another, and where they meet is a tectonic boundary. And tectonic boundaries explain earthquakes, mountains, ocean basins, and volcanoes. So that's what we're getting into here. Most of the volcanoes we see are interplate. That means they occur at a plate tectonic boundary. The most specific places we see this are convergent boundaries and divergent boundaries. Transform boundaries, our third type of plate tectonic boundary, have horizontal movement with no vertical movement. Therefore, no magma is generated, thus no volcanoes. Convergent and divergent boundaries both have processes associated with them that generate magma by melting rock, that creates a melt that is less dense than its surroundings, which ultimately comes up to the surface and volcanoes. We also have volcanoes that are not associated with plate tectonic boundaries. These are intraplate volcanoes, and the name we give these are hotspots. The most famous of all being the Hawaiian Island chain, a supporting line of evidence that helps us provide the evidence necessary for plate tectonics. Another famous hotspot is Yellowstone. Both of these located very far away from any tectonic boundaries, but active volcanoes. So we've got two locations where volcanoes can occur. One is going to be at boundaries, and it's going to be either divergent or convergent. These are interplate. We also have at hotspots, which are away from any plate tectonic boundaries. This is a nice figure. It would take me a long time to draw, and I wouldn't do half the justice. So volcanoes and plate tectonics. Here we see the rigid lithosphere lying on top of the ductile asthenosphere. These are Earth's physical layers by physical characteristics. A solid, rigid lithosphere, broken into tectonic plates, floats on top of a ductile asthenosphere. Now, here's a convergent boundary. Oceanic crust subducts underneath continental crust, and we get the process of flux melting, creating a line of volcanoes called a continental volcanic arc. Here we have crustal thinning, creating a continental rift, divergent plate boundary, and associated volcanism. A mid-ocean ridge, divergent plate boundary, the center of all the oceans. This is how ocean basins open, and associated volcanism. We'll move over here to oceanic crust, convergent plate boundary. We have the older oceanic crust subducting under the younger, and volcanoes occur. Here we have an island volcanic arc. And our last type, so those were all boundaries, convergent, divergent, convergent, divergent. But then over here, away from a plate boundary, right here in the middle of oceanic crust, we have a hot spot, a plume of hot material that rises up to the surface and erupts lava, creating a volcano. Great. This was a nice little overview. Let's get into them a little bit more. Continental rifts are characterized by volcanoes. This is a divergent plate tectonic boundary. It's essentially 299 million years ago, all of the continents came together. About 180 million years ago, they started to split up. That continent was Pangaea, the last great supercontinent. And when that continent started to split up, it began to do so by continental rifting. So this is the basin and ranges. It's a nice big wide valley, and what we see here is a cinder cone that's popped up right in the middle of it. Very common for the southwestern portion of the United States. Also, East Africa is splitting in two near the Red Sea. The Red Sea is a divergent plate boundary, but then through Eastern Africa, we have the East African Rift Basin, and with it also associated volcanism. So we have these, this is a model, obviously this is not real life, but our models come from what we observe on the land. Geologists go out, they study the landscape, they make observations that are as objective and free from bias as possible, and then they put all of the information together to create a dynamic model for how our Earth works, and it really all comes together with plate tectonics. Okay, the driving force for volcanism is plate tectonics. Got it. Perfect. Let's keep going. Divergent plate boundaries. So these are mid-ocean ridges. If we see over here, I'm a little bit far away, but here's the East Pacific Rise. It wraps around underneath Australia, comes up the other side, and then the Mid-Atlantic Ridge separates Africa, South America, North America, Europe. 40+ thousand miles of underwater volcanic mountain ranges. It's the longest mountain range on Earth. And as the plates diverge, decompression melting occurs, releasing the pressure and causing hot mantle rock to rise to the surface. The primary rock type here of oceanic crust is basalt, a mafic, igneous, extrusive rock. There's a little bit of classification for you. And as this basalt erupts, it erupts to form these underwater features called pillow lavas because they look like pillows. It's time for a rest. They also look like if you ever throw a marshmallow onto a fire at your campfire. Next time you're making s'mores, sacrifice one of these s'mores in the name of science. Throw that marshmallow onto the fire, and it will start to form a crust on the outside, and then it'll break through the crust and bubble and expand, and it is remarkably similar to pillow lavas. Let's keep going. Mid-ocean ridge, global distribution. Here's the seams that wrap around the entire Earth, or the ridges that wrap around the entire Earth, like the seams of a baseball. So this is a lot of mid-ocean ridge that's occurring. Whole Earth. So I like an image like this because what it shows is that these are not localized features, but a driving force. Plate tectonics helps us to understand, but plate tectonics leads to volcanism, and there is new Earth being generated every single day, all of the time. The bottom of the oceans, we don't even know it because we don't usually hang out that deep in the middle of the ocean for very long or any time at all, really. With hydrothermal vents, this is just kind of a special shout out, a little tangent off of volcanoes, but associated. So mid-ocean ridge volcanoes actually will heat up water. Bottom of the ocean, lots of water. As seafloor spreading occurs, there are cracks and fractures in the oceanic crust that the water seeps into. That water is heated by the hot mantle material, superheated, dissolving minerals, and these minerals eject in what are called hydrothermal vents because they emit various colors of smoke based on temperature. And these hydrothermal vents support communities at the bottom of the ocean that do not use photosynthesis. The light from the sun only penetrates about 1 kilometer or 1,000 meters down into the water column. But here we're going many thousand meters deep, well beyond where light can reach, and there is still life down here. Maybe one of the first places life began in these hydrothermal vents, very symbolic of early Earth conditions when there was no oxygen in the atmosphere. How did life begin without oxygen in the atmosphere? Well, maybe by not using oxygen in the atmosphere is one thought. So the energy is not through photosynthesis, it's through chemosynthesis. This is a pretty cool thing. And so when we look at the distribution of hydrothermal vents, and these are relatively short-lived. Hydrothermal vents don't persist forever, but they do. They come up and they have a lifespan and then they go away. They're located all over the mid-ocean ridge system, which is really cool. So not only do plate tectonics explain why we have mountains and earthquakes, but quite possibly they could also explain how life first developed on Earth. And realistically, without plate tectonics, we don't have the recycling of biogeochemical cycles of our oxygen, carbon, and nitrogen that are creating an atmosphere that is habitable for life to exist. So thank you, plate tectonics, and thank you, volcanoes. Okay, let's keep going. That was divergent. Let's go down the list. Convergent. When we're thinking about convergent boundaries, which is like this, when two plates move towards each other, we're thinking about the process of subduction, where one plate descends underneath the other. In a continental-continental collision, both plates go up. You don't really have volcanism because the processes that generate magma are absent. But in a subduction zone, where oceanic lithosphere descends underneath continental lithosphere, flux melting occurs, and you have the rising of less dense material to create a chain of volcanoes. When this chain is over or in continental crust, it's a continental volcanic arc. If we're to replace this continental lithosphere with oceanic, it becomes a volcanic island arc. Moral of the story is that convergent boundaries and the process of subduction leads to volcanoes. So why do we have volcanoes? Plate tectonics. Where do they occur? At plate tectonic boundaries. Why? Well, for divergent, because of decompression melting, and convergent because of flux melting. So now we're getting to concepts, theories, mechanisms, and processes. I love it. When we start to think about science in a certain way, we can become process-based oriented. Well, what is the process that this occurs? What is the mechanism that initiates the process? And what is the concept that we're trying to understand. Right now we're thinking about the dynamics of Earth's surface processes. So, okay, global distribution, where are they? The Pacific Ring of Fire is a horseshoe-shaped belt that surrounds, circumvents the Pacific Ocean. The Pacific Ocean being the largest ocean of Earth's 5 oceans, and it is surrounded by convergent boundaries of both oceanic and oceanic crust, oceanic and continental crust, oceanic and continental crust, characterized by all kinds of volcanoes, and with those volcanoes are earthquakes. Earthquakes are, how do I want to put this? Earthquakes help us see with a blindfold on. They help us understand what's happening underneath the surface of the Earth. This model is heavily supported by earthquake information. We will go deep into earthquakes, but not for now. I want to. I really do. But let's stay on task. The Pacific Ring of Fire, all the way around Australia, East Asia, north of the continent or north of the hemisphere, down North America, South America, global earthquakes. When we map out large earthquakes, it pretty much makes that exact trace of the Pacific Ring of Fire. Convergent boundary subduction zone earthquakes are the largest earthquakes on Earth. And when there is an earthquake, there's movement of the descending slab underneath of another slab of crust, leading to the creation of volcanoes. It's all connected, especially when we're talking about geology. Volcanoes at boundaries, divergent and convergent. But what about volcanoes that are in the middle of a tectonic plate? Well, there's a lot of them. Hawaii, smack dab in the center. Yellowstone, couple on Australia. Many earthquakes in Africa. We've got some over here in East Asia. Lots of earthquakes. Earthquakes? I guess I'm stuck on that topic. Lots of volcanoes, globally distributed, that do not have anything to do with plate tectonic boundaries. So, how do we explain this? Well, what our model shows is that there are certain, I'll stay here and explain it. There are certain areas where instead of having a plate tectonic boundary, this magma chamber, we also call it a mantle plume, remains stationary. The mantle plume remains stationary, and we'll call this oceanic crust or continental crust. We'll move over the mantle plume. Magma is generated in a location that is away from a plate tectonic boundary. The overlying crust moves over that spot, and this is how we can get a series of volcanic islands. I explained the mechanisms of this in hotspot volcanism. The big island of Hawaii, and then all of the Hawaiian islands moving over and away, Maui, Oahu, Kauai, progressively older. The mantle plume in Hawaii stays here as the Pacific plate is being pulled this direction because of the processes of subduction on the Pacific Ring of Fire. Same thing in Yellowstone. Here is Yellowstone, and we can see volcanic deposits in Yellowstone about 500,000 years ago, 750,000, 6.4 million, 10.7, 12, 15, 16.1. So what's happening is the hotspot is underneath Yellowstone. So where Yellowstone is currently, in the mantle is the location, and that is not moving. But the North American plate, we'll go here like this. Hotspot stays the same. This is the North American plate. The North American plate is moving over that mantle hotspot. Pretty cool to explain where volcanoes happen, both at boundaries and away from boundaries. I don't think it could be complete to have a lecture on volcanoes without looking at a volcanic eruption. And so here is Mount Kilauea on the Big Island of Hawaii. That is an active volcano, and it erupts often. This is from January 5th, 2023, and it has been continuing to erupt, continuing to pose hazards and risks to humans, property, and the environment. We discussed that in volcanic hazards. The Big Island of Hawaii is a shield volcano. There are 3 types: shield, composite, and cinder, of which we'll talk in another lecture. Also, to have the completion for volcanoes. So volcanoes are when magma erupts on the surface of Earth as lava. They create an igneous extrusive rock, and they are globally distributed. We see them at tectonic boundaries, both divergent and convergent, and we see them away from boundaries at hotspots. The driving force for why volcanoes are created is plate tectonics. It is the movement of heat in Earth's interior that creates our dynamic model for how mountains are built, ocean basins are created, volcanoes form, and this leads to various types of volcanoes all over the Earth, posing various types of hazards to you and I. Thank you so much, and I'll see you again.